Since January 2015, Fulnek School's Physics Department have been involved in an Erasmus Plus funded seismology project in cooperation with 3 other European schools.
Our primary aim is to design a low-cost seismometer suitable for use in developing countries.
The aim is to make science more widely accessible to young children who might not otherwise have access to learning facilities. We decided to get involved with the project because not only was it good experience for us, but incorporated scientific and cultural education.
Inspired by the TC1, our design takes an everyday household item and turns it into a functioning seismometer.
It was difficult to decide on a model, but the Pringles can mimics the basic design of the TC1.
Our design uses a pendulum suspended by a screw consisting of a transducer connected to a mass. When the pendulum moves, the transducer produces a small current, which is then processed. This current is generated when the pendulum moves and the kinetic energy is converted to electrical energy.
This is then processed by the digitizer, which receives the analog signal produced by the transducer and plots a graph using samples of the data.
It is important to take into account the optimum frequency, which can be affected by various factors. This equation relates the time period of the pendulum to its length and to the gravitational field strength.
When seismic activity occurs, the signal from the seismometer is processed through a digitizer and displayed by the software Germasize as a graph.
We were inspired by the late earthquakes in Nepal that had devastating effects. We carried out detailed analysis of these earthquakes and presented them to spectators consisting of both scientists and of members of the public at the science fair we attended on our seismology trip to Nice in October. Our original design was a compound pendulum that had a mass suspended from the transducer on a rigid rod. We found this only produced a binary signal.
After incredibly thorough inspection of all mechanical aspects, we identified the problem as 2 wrongly placed wires, and our second attempt mirrored the first entirely, with the exception of the switched wires.
Our current model replaces the rigid rod with a piece of string and isolates the advantages of a digitizer. We would expect a more precise signal.
Technical difficulties were experienced.
In an attempt to rectify this, we sought the expertise of Ted Channel, the master behind the TC1 design. We Skyped him from his home in Idaho to seek expert scientific advice, as he'd been generous enough to provide all necessary components for our seismometer and ship them across the Atlantic to our school in Leeds.
After checking the circuit board of the digitizer, he provided us with the codes to install.
Our problem was solved after installation of the codes. Our low-cost seismometer is now ready for use in India.
This project has given us the opportunity to be educated in computer programming, more specifically in Python and using a Raspberry Pi.
Not only this, but we also had the chance to meet some great new people from Nice in France, Naples in Italy, and Torquay in England. Thank you for watching.